Welcome to the lecture on Chemical Kinetics, which is Chapter 14. When we start talking about chemical kinetics, we're really kind of interested in the rates of different chemical reactions. So we want to know how fast these reactions proceed. And so whenever we talk about chemical kinetics, we're really looking at the rate of a chemical process. And even more so, we're thinking about reaction rate, which is just the speed of a chemical reaction. So we combine two reactants together, and we want to know how fast that reaction can proceed, which is the reaction rate. And the chemical kinetics is just the study of those rates for these different chemical processes. And so when we think of a rate of a reaction, it's really determined by two things. One is it monitors the change in the concentration of either the products or the reactants as a function of time. And so we're going to talk a lot about the reaction rate as a change in concentration per unit time. And so reaction rates can be affected by a number of different things, four in particular. One is the physical state of the reactants, depending on what the state of the reactants are. Gases mix a lot easier than two liquids or two solids, and so the physical state of the reactants can help determine the reaction rates. The concentration of reactants. The higher the concentration, the more likely that these reactants can bump into one another, causing a reaction to take place. And so the rate of that reaction is going to speed up with the higher concentration of reactants present. Third is temperature, and when we think of temperature, we can think about as we increase the temperature, the molecules move more rapidly, which means they bump into one another more often, and we get more reactions taking place. And fourth is catalyst, which we'll talk about later in this chapter. So when we think of a reaction rate, it's really not that different than thinking of speed of a car, right? In speed of a car, we want to know how far you've gone over time. And we always say it's meters per second. So we measure the meters that we covered over time in seconds. Well, speed of a reaction is really not that different, because here we're looking at the concentration per time. So the molarity per second. So if we start off with a reaction where we say it's a hypothetical reaction, A goes to B, and in this reaction it's irreversible. It only goes in one direction. And so in a 1 liter flask, we dump in 1 mole of reactant A. And over time, reactant A is going to convert into reactant B based on this chemical reaction. And so over 20 seconds, we see that we went from 1 mole of A to 0.54 moles of A, which means the other 0.46 is now moles of B. And over another 20 seconds, and now we're at 40 seconds total, we see that 1 mole of A is now down to only 0.3 moles of A, and we've now increased the concentration of our product up to 0.7 moles of B. And so when we look at the reaction rate for this reaction, we could look at it in two different ways. The rate of appearance of product B, so how much of product B is being produced over time, or we could look at the rate of disappearance of reactant A. So when we think about the rate of appearance of product B, it's the change in concentration of B divided by the change in time. So we really have delta, and then we should have these brackets around B, like these, which is the concentration of B. So the change in the concentration of B divided by the change in time. Now for the rate of disappearance of reactant A, we actually add a negative sign in front, because that's going to make sure that we end up with a positive rate. We can't have a negative rate. We just show the negative saying that it's disappeared, that we're losing that. And so in either case, we could calculate the rate of appearance of product B over 20 seconds or over 40 seconds, or we could look at the rate of disappearance of A over 20 seconds or 40 seconds. Now this all brings us to the collision model theory. And so really we have to think about how a reaction proceeds. So one, those reactants must make contact between one another. They need to bounce into one another. And the more they bounce into one another, the greater that reaction rate. The contact between those two reactants must lead to some kind of bond breaking. There has to be a sufficient energy that bonds are broken and that new bonds could end up being formed. Third is the reactants need to be in a suitable orientation. They have to hit in a precise orientation for the reaction to proceed as it should. And so really the take-home theory of collision model theory is the greater the frequency of collisions, the higher the reaction rate. Okay? The more those molecules bounce into one another in a suitable orientation, the faster that reaction is going to be. So if we look at an example Here we have butyl chloride reacting with water to form butyl alcohol and hydrochloric acid. And if we measure the concentration of butyl chloride, the starting reactant, over time, and we measure how much of that reactant is left, we can then determine what we call the average rate of the reaction. And so from 0 to 50 seconds, we see that the concentration of butyl chloride drops from 0.1 down to 0.0905. If we take the change in concentration of butyl chloride divided by the change in time, we get this average rate, which is 1.9 times 10 to the minus 4th molar per second. We could do this over a range, and we could look at from 0 to 800 seconds, we could look 0 to 400 seconds, and we're just going to take the difference in the concentration between 0 and 400 seconds divided by the change in time. And so what we see is that the average rate as the reaction proceeds actually decreases. It gets slower and slower. And that's because more and more of the reactant molecules are being used up and being converted to product. So as products produced, we get less and less of the reactant available, which means we're going to lead to fewer collisions between those reactant molecules. Thus, we lead to a lower average rate for that reaction to proceed. But we can also talk about the instantaneous rate of a reaction, which is just the rate at a particular instant during the reaction. And we could say this is equal to the slope of the curve at a particular time. If we were to look at the instantaneous rate at t equals 600 seconds, well, that's right here at this point. Well, the only way we can calculate the instantaneous rate at t equals 600 seconds is imagine that we draw a tangent line here that just touches at t equals 600 seconds. And then we can just connect those by making a triangle. Well, this triangle is the change in butyl chloride, which is measured on the y-axis, and the change in time, which is measured on the x-axis. And so if we look at the instantaneous rate for a reactant, we know we have to have a negative sign in front. And so we could look at the change of the reactant concentration divided by that change in time, and that's going to give us our instantaneous rate at this point. Now you could draw these lines further out, you could make them shorter, but at the end of the day we need to make a nice triangle here, where we can measure the change in butyl chloride versus the change in time. So from here on out, anytime we talk about the rate of a reaction, we're talking about the instantaneous rate, and sometimes we talk about the initial rate, which is the instantaneous rate at t equals 0 seconds, at this very initial part of the reaction. So far, we've only talked about reactions where it's a one-to-one stoichiometric relationship. But there's reactions where the stoichiometry is not one-to-one. And for those type of reactions, we designate it with this kind of nomenclature. Well, if we wanted to look at the rate for a particular reactant or particular product, or in relation to a particular reactant or product, then we can use a slightly different equation. It's still the change in the concentration of A, but we're dividing that by the stoichiometric coefficient, little a, times the change in time. Well, for reactants, like we said, we have a negative sign in front. Okay? And then for the products, we do the same thing. And so we can see that we can relate the rate of a reactant to a product, or a product back to a reactant, or two reactants together, or two products. And we have a couple practice problems that focus on that. So in this practice problem 14.1, we say, based on the following figure, order the following three states from fastest to slowest. And so we have three choices. One is the average rate between 0 and 600 seconds. Second would be the instantaneous rate at 0 seconds. And third, the instantaneous rate at t equals 600 seconds. And I say you do not need to use any calculations. So you can pause the video and think about the answer. Okay, the reason you don't need to do any calculations for this is you can just look at the slope of each of these lines. And think about the slope of the line as the greater the slope, the faster the reaction rate. And so if we look at the slope for t equals 600 seconds, see it here, but at 0 seconds we see it's much steeper, which says it's going to have a greater rate than at 600 seconds, which makes sense because as a reaction proceeds, it's going to slow down. You're using up more of the reaction, or reactant, And so the reaction gets slower and slower, and we see that in this curve. Sorry. Then we look at the average rate of the reaction between 0 and 600 seconds, and what we see is that that slope of that line is going to be less than the 600 seconds, or sorry, greater than the 600 seconds, but less than that of the 0 seconds. And so our answer is going to be C. We could also look at other practice problems where we can relate the rate of one reactant or product to another reactant or product. And so in this practice problem, 14.2, we're considering the reaction above, where you're given the rate for reactant A2, and I want you to find the reactant, or the rate for reactant B2. Pause the video and solve the problem. Okay, so what we see is that the answer is going to be D, where it's going to be 3 times that of the rate of A. In practice problem 14.3, it's the same kind of idea. If we know that oxygen is decreasing at 0.23 molar per second, what is the rate of water increasing? Well, it's 2 times that of the oxygen, but it's going to be positive because it's increasing, and so it should be 0.46 molar per second. That concludes chapter 14 for this time.